Okay, hi. Today I'll be speaking to you about what are called field theories. So I'm not going to recap the motivation for doing what we're doing, but the idea broadly is that we want to model population dynamics, and we want to model in particular how populations of individuals evolve. And we said, okay, a good way to do this is to start from first principles using something called the stochastic birth death process. So for example, if we had a population of identical individuals, in this case redbirds, we say that we can characterize this population using a number, just the population size, and then uh, observe that this population changes either through birth or through death and nothing else. In this case, we say that we parameterize the birth rate and the death rate with two functions, b and d. But this is probabilistic. That is, these are finite populations and birth and death occurs with some probability. We then wanted to describe this process mathematically. And we did this by saying that the probability of finding the population with a given size n at time t can be calculated by looking at the rate at which probability flows into the state minus the rate at which the probability flows out of the state. What does this mean? This means, for example, if we have a state n, we can count the number of ways we can exit this state, which I've shown in red here, and the number of ways we can enter this state, which I've shown in blue. And then say that dp by dt, the rate of change of probability of being in this state, is rate of outflow times probability of finding this state subtracted from rate of inflow times the probability of finding all the inflow states. Mathematically, it looks like this. So for inflow, we have from the state n minus 1, you can go to the state n at rate b of n minus 1, and the probability of finding this state is p of n minus 1 comma t. And similarly, you can also flow in from the state n plus 1 through the death of an individual. This is parameterized by d of n plus 1 times the probability of finding this state, which is p of n plus 1 t. We can also calculate the outflow. Similarly, given the state n, you can exit this state through the birth of an individual, which occurs at rate b of n, or through the death of an individual, which occurs at rate d of n. We then rearrange this slightly using something called a step operator, delta. Here delta plus or minus just moves the population up or down by one individual. And this allows us to find uh, a compact representation for dp by dt, which we call the master equation. To proceed analytically, we assumed that there is something called a system size parameter. Explicitly, we assume that there is something like a carrying capacity k, which puts a bound on population growth, such that if the population size exceeds k, growth rate is expected to be negative. What this looks like, for example, is here are some simulations of a logistic equation where I have a stochastic simulation in red, and the dotted line is the actual deterministic logistic equation for various values of k. And what this will look like is the stochastic simulations fluctuating around the deterministic state. So here, if k equals 1000, the total population size starts to fluctuate somewhere around 1000 individuals. And we observe that as k increases, even though this magnitude of fluctuations is the same, notice that the y-axis keeps changing in scale. If you sort of squint at it and normalize by k, the fluctuations look smaller and smaller, and the process seems to get more deterministic. We can exploit this mathematically by saying that instead of population numbers, n, we will look at population densities by dividing by this carrying capacity. And what this means is that we can translate the master equation as well from n to n by k, which I'm denoting by x, just by transforming variables. And if we do this, We said then, since the population now transitions in units of 1 by k, I can sort of Taylor expand functions that look like this, functions that look like x plus or minus 1 by k, and this rescaled process was easier to handle mathematically. In particular, if we now Taylor expand these step operators and then rearrange, I'm not going to show you how it's done because I've done this in a previous class, we will arrive at something called the stochastic differential equation. This stochastic differential equation looked like this. It said that there is a deterministic term, dt term that is, which captures the growth rate, the difference between the birth and death rates of the population. But there is also a stochastic term for finite populations that scales inversely with the square root of carrying capacity and is proportional to the sum of the birth and death rates. We also mentioned that this first term, b minus d, controls the mean behavior or the expected behavior, and this b plus d by k is the variance in the change in density. What this looks like is the following. It means that even if two systems have the same deterministic growth rate, if I just add a constant, this term changes, but the first term does not. For example, here are two simulations of the logistic equation in red and blue, where b minus d is the same, but I have added a constant to the blue population so that b plus d is greater in the blue populations than the red. And what it will look like is wild fluctuations in blue that are not present in red, even though they have the same expected growth rate. And you can maybe see that I've simulated multiple realizations here, and the blue realizations hit 0 quite often. So here are some, here's another one, here's another one. And so these blue populations tend to go extinct just because of stochastic fluctuations, even though red and blue have the same growth rate. This is all well and good. And what I actually showed you on the board last time was that including more discrete traits is easy. For example, if we had red and blue birds instead of just red birds, we can characterize the population in a similar way. We now have two numbers counting the number of red birds and the number of blue birds, and four functions, two representing the birth and death rates of red birds and two representing the birth and death rates of blue birds. We then, as before, can count which transitions are possible and do this mathematically with the master equation and have our Taylor expansion that I showed you just now. And in fact, if we had 3 birds or 4 birds, the same procedure goes through, right? So if I also had red, blue, and green, I would have one extra number here and two extra functions, but the same procedure goes through. There is no essential technical difficulty. And this applies if I have any finite number of birds. But these traits like color that I've been talking about so far are discrete. That is, a bird is red or blue or green, but never orange, let's say. But what about quantitative traits? After all, many traits in fields like behavioral ecology are under the influence of a very large number of genes and or epigenetic factors, and so appear to vary quantitatively. For example, beak length, we may expect to take all values in some interval, like 0, 1 or 0, 2. And so we can't really list out all the possible values here. That is, we can't find a finite list such that this list has every possible beak length, because a beak length could be 5 centimeters or 5.1 centimeters or 5.01 centimeters or 5.001 centimeters and so on. How do we speak about such traits? We would like to, because they're important in many cases. Now, in this case, since each individual has some unique trait value, the population looks like sort of a cloud of points instead of just a vector. So if we look at the trait value through time, we might see some cloud representing the population that evolves. Here, each dot is an individual, and there's a very large number of dots, as you can see. And in particular, what I wanted to show you here is that with quantitative traits, the population can explore new areas of trait space, and it can do very interesting things. For example, I could have a population that's initially largely monomorphic, meaning that this distribution is unimodal, and it can evolve to become polymorphic over time. This is called evolutionary branching. And these sort of phenomena are interesting, and we would like to model them for finite populations. Now, if I look at a slice of this population, if I look at a particular time, each individual is definitely a unique trait because these are quantitative. But if I bin them, if I bin these trait values, let's say look at what is between 0 and 0.2, what is between 0.2 and 0.4, and so on, I will end up getting some histogram. And the idea here, the idea that I will explore, is that maybe if I have a very large number of individuals, I can approximate this sort of histogram with some continuous function. Continuous function that varies over time and space. The physicists call a field, which is why this is a field theory. But this is the idea. The idea is that we don't know how to handle just a cloud of discrete points because it's complicated. If we try to make a list of all possible individuals, the length of this list can change over time because the total population size can change. But if I have a nice function, maybe I can play around with the function and get some useful insight from it. So this is what we will try to do. Let me now finally get more explicit about the biological setting. I'm going to consider a finite population of individuals that have traits which are quantitative and take values in some abstract trait space, which I will call T. I will assume that this is one-dimensional, so that each quantitative trait of a given individual is just a number. So if you want intuition in your head, beak length is a good example, human height is a good example, let's say beak width is also a good example, but I am not considering two-dimensional traits or three-dimensional traits. I will allow the total population size to fluctuate over time. Stochastically, naturally, I am not going to put any constraints on the total population size. That is, my model is not like a Wright-Fisher or Moran model, where the total population size is strictly constant. I will, however, assume that the trait value of an individual cannot change over its lifetime. So, for example, I'm not allowing phenotypic plasticity. I will also assume that changes in the population are only through birth and death of single individuals at a time. What does this mean? This means, for example, I am not considering variable numbers of offspring that are born at the same time. I am also not considering situations where one type can mutate into a different type. That is sort of like saying the trait value of an individual changes over its lifetime. These sort of things I will not allow. Finally, I will also assume that there is no extrinsic noise. That is, there is no stochastically fluctuating external environment that can cause fluctuations. All noise instead is due to the finiteness of the population. So with this setting, let's try to characterize our population again from first principles. Since the trait value of an individual can't change over its lifetime, and an individual has exactly one trait, a somewhat natural way to characterize the population is using what's called a Dirac mass. What's a Dirac mass? Well, if I look at one bird in my population of birds with varying beak lengths, it has one exact value of beak length, let's say pi centimeters. And we can therefore characterize this bird by placing something called a Dirac mass. The physicists call it a Dirac delta function at the value of its trait length. So here the idea is that the bird has a beak length of x, and we characterize this by placing this little object called delta x, which is defined as follows. If I have any set A which is a subset of my trait space, and any nice function f, and I integrate f times delta x over the set A, I will recover f of x if x is in A and 0 otherwise. This is how I am formally defining this Dirac mass. I may use the word function for this informally later on, but the mathematically rigorous way to view this is as something called a measure. You don't have to worry about what that is if you don't know, but the whole idea of this talk is to provide some heuristics to try to formalize certain processes that are measure valued. Now, let's try to get some intuition for what this Dirac delta is. Sometimes people like to think of it as an infinitely thin, infinitely tall normal distribution, and this is valid, but I prefer to think of it as an indicator function. What does this mean? This means, for example, from the definition, since this is true for any nice function f, I can choose f to be identically equal to 1, which gives me that the Dirac delta integrated over a set A gives me 1 if the bird is in the set A and 0 otherwise. So if I look at regions of trait space and I pick some region, let's say I look at birds with beak length between 0 and half. If my focal bird does not lie in this set, I will get 0 if I integrate over the set. If I look at some other set that contains the bird, I will get 1. So this integral or this delta is just telling me, given a set, does this set contain my focal bird or not? That's all it's doing. Notice in particular that if I integrate over the entire trait space, I must get 1 because the bird must be somewhere. And we can use this to find the total population size, as I'll show you. This is how I like to think of the Dirac delta, and I think this is how you should think of the Dirac delta. It is never going to occur outside of an integral in our talk. So this definition suffices. Now that we can characterize a single bird as a Dirac mass, we can characterize the total population as the sum of a Dirac mass. That is, for every bird in the population, we will place a Dirac mass at its trait value. So if there is a bird with trait value x1, I will place a Dirac mass at the point x1. If there is a bird at trait value x2, I will place a Dirac mass at trait value x2, and so on for every bird in the population. So I can characterize the population as a whole by this entity, which I'm calling nu, which is a sum of Dirac masses. Some basic properties of nu follow. For example, from the definition of the Dirac mass, if I have any function and I integrate f times nu over the entire trait space, this means evaluating f at the point xi for every xi in the population. In other words, if I integrate f times nu, where nu is the population over the trait space, this is the same as evaluating the function for every bird present in the population. It is also true by just setting f identically equal to 1 that if I integrate this over any subset A, I will return the number of individuals with trait values in A. This again follows from the definition of Dirac mass because each individual Dirac mass is an indicator. Like I said, it gives you 1 if and only if that bird is in A. Integrating over the entire trait space therefore gives you the total population size at time t, which I will denote by nt. This is how I will choose to characterize my population, not as a list of numbers, not as a vector or a matrix, but instead as this thing, this sum of Dirac masses, which you can intuitively think of as a function if you like, but properly is something called a finite measure. We can now describe how the population changes now that we've described what the population looks like. By the way, you guys can stop me.
Have a
Yeah.
question. Yeah.
Sorry?
So yeah, in the graph you draw there. So it looks like the different Dirac masses have different heights, if that has any meaning. Or
Yeah, so the meaning, uh, there is no formal meaning because they're all infinite height if you try to draw them. Informally, what I wanted to convey is that the xi's in this sum need not be distinct. So for example, I could have two birds that have the trait value x2, in which
oh, I
case
see.
this
Okay,
sum will look like delta x2 plus delta x2.
I see.
This is allowed. I am not constraining each trait value to be distinct, is what I wanted to convey. But you're right, the
Oh,
heights are meaningless because they're all sort of infinitely tall.
okay, thanks.
So once we have described the population, the next step is to describe the dynamics. And we will do this, as I said, by assuming that there is only birth and death and nothing else, and try to describe from first principles how the population should change. Now, since each individual is characterized as a Dirac mass, birth corresponds to addition of a Dirac mass to the population for some trait value, and death corresponds to the subtraction of a Dirac mass, again for some trait value. And I will assume that these are the only transitions allowed. My stochastic process, therefore, is taking values in the space of all sums of Dirac masses. That is, at a given point, my stochastic process is a function, whereas before it was a number for discrete rates or a vector if I had many discrete rates. The state space is not this now. It is this M of t, which is a sum of Dirac masses, right? And in particular, this is infinite dimensional. We therefore want to describe how a function valued stochastic process changes because we are characterizing our population itself as a function. We can do this as we did before using birth rates and death rates. I will therefore assume that the transition nu to nu plus delta x occurs at a rate b of x given nu. This quantity is a function. It takes in two arguments. The first argument is a number. It is a trait value. The second argument is a function. It is the population. And it outputs some rate, that is a number between 0 and infinity. Notice that one of the arguments of B is a function. Such functions that take in functions as inputs are sometimes called functionals. They're sometimes also called operators. So I might use these words, but it's just a function. What do I mean by rate? Again, we should be precise because remember, this nu and this delta x we only defined inside integrals. So it pays to be precise about what a rate is here. And I will tell you, here I mean that the probability that if I know that nu has changed to something, whatever this something may be, the probability that what happened was the birth of an individual that had trait value lying in a set A is given by integrating b of x given nu over the set A. By the way, I have chosen this notation intentionally. This bar, you can think of it, I mean, it's not meaningful beyond just a comma. I wanted you to read this as the birth rate at a given trait value in a given population. So this is why I am using the bar to use so that I can read it as b of x given nu, but it is an argument of both x and nu, this function. I can also say that there is a death, again with a death rate, which once again takes in two quantities. It takes in a number and a function and outputs a real number. And this death again is characterized by saying that if I know something has happened to nu, the probability that the something was the death of an individual that had trait value lying in the set A is the integral of d of x given nu over A in the x variable. I am integrating in the first variable, which is a number. The normalizing constant in both cases is the integral of b plus d over the entire trait space. And of course, I will assume that these are finite. And you can check that these quantities are equivalent to saying that birth and death are the only things that can happen. You should think of this maybe as the continuous analog of what we had for discrete traits, which was where we had a sum in the bottom, except now we have integrals on top as well. And this is just because our population and our individuals are defined in terms of quantities that cannot occur outside integrals, that are not really well defined outside an integral. So this describes our population in principle, but we don't have an idea of what is going on yet. And we will try to describe our stochastic process the way we did before. To do this, remember we just said there is birth at rate b of x given nu in a population nu at a point x, and the death rate of individuals at the point x in a population nu is given by d of x given nu. This was our assumption. I will call p nu t the probability of finding the population in a state nu at time t. I am going to assume that this exists. That's a stronger assumption than you might think, because this nu is a function, and so this probability is defined on some function space. And it turns out, though I'm not going to show it or prove it or do anything of the sort here, that when we have one-dimensional traits of the form I'm considering here, this sort of function usually exists. But if I have two-dimensional or higher dimensional traits, you typically can't even find this sort of function. This is called a density function. You cannot find a density function in two or more dimensions very often. But in one dimension, we're okay. This is why I'm restricting myself to one-dimensional traits. We would like, given that this function exists, to find an equation for it, because it describes then what is the probability of finding some particular population at some particular time. We will do this using the same trick as before. We will say that dou p dou t can be calculated as the rate of inflow of states minus the rate of outflow of states. Okay, can we calculate the rate of inflow and outflow of states? Yes, we will do it the same way we did for discrete traits. And someone should tell me if I'm going too fast. We will calculate first the rate of inflow as follows. Given a state nu, how can you enter the state? Well, you can enter the state from a population that looks like nu minus dx, delta x, through the birth of an individual at the trait value x. And this occurs by assumption at rate b of x, that is the birth rate at the point x in the population nu minus delta x. So if I calculate my rate of inflow, I can calculate it as this transition rate times the probability of finding such a population in the first place. So the rate then is the probability that I find nu minus delta x in the population. I find the population nu minus delta x times the rate at which nu minus delta x transitions to nu, which by our construction is this birth rate function b of x given nu minus delta x. You can also enter nu through deaths. If I have a population of the form nu plus delta x and one individual at the point x dies, I will enter my state nu again. And this happens at rate d of x in the population nu plus delta x, because this is the death rate. Once again, our rate of inflow is therefore d of x given nu plus delta x times the probability of finding such a population, which is nu plus delta x at time t. But notice I care about this population nu, and this transition is true for a particular x, right? But this can happen for each x in the trait space. This transition still holds for any given x in the trait space if type x is born and this population exists, we will end up with the population nu. So to find the total rate of inflow, we need to integrate over the entire trait space. We need to integrate over every possible x. It's possible that for many of these, the transition rate is 0, but we are not imposing that constraint ourselves. We will let the system do it. For example, one might assume that some of these transitions are just not possible at all. If there is no individual at trait value x, we would want d of x given nu plus delta x to be 0. But I will assume that these functional forms capture all of these little nuances. I don't need to do it here. And so I will integrate over tau, over t, to get all possible rates. And this gives me the total rate of inflow into nu. I can also calculate the rate of outflow in a similar way. Given a population nu, I can flow out of this population through birth of a type X individual, which is a Dirac delta at X. And this birth happens at rate B of X given nu. I can also transition through deaths from nu to nu minus delta X at a rate D of X given nu. I can therefore write the rate of outflow as, once again, the transition rate B of X given nu times the probability of finding this population, which is P of nu given nu comma T. And for the death rate, the transition rate from nu to nu minus delta X is D of X given nu, and the probability of finding the population nu is P of nu T. Notice that once again, this is true for each X in the trait space. And so to find the total rate of outflow, we will need to integrate over all possible trait values. Okay, we have rate of inflow, rate of outflow. And because we assumed that the population transitions in units of one individual at a time, these are the only possible transitions that we can have. Right? If we had some other transition, the transition rate must be 0 because of our assumption. We can now go back to our population, nu, and calculate how dp by dt changes. We said that dp by dt should be the rate of inflow minus the rate of outflow. And we have now calculated the rate of inflow and rate of outflow by counting transitions. Therefore, we can just calculate what dp by dt is. I will use the same notational trick I did earlier by defining what I call step operators. Here I'm denoting it by e sub x plus minus, and given any functional f that is a function of the trait space and the population, this step operator tells me what the value of the function would have been at the same location in trait space if the population differed by one individual at that point. That is, for example, if f is a birth rate, E plus of the birth rate at y in a population nu is the birth rate at y in the population nu plus delta x. I need this just so I can rewrite the rate in these things because they are of the form of populations that are 1 Dirac mass away from our focal population nu. If I now compute R in minus R out, here's what happens. I have color coded the terms. Here the first term we have B of x in a population nu minus delta x times P of nu minus delta x at time t. This I can rewrite with my step operator as E of x minus, which is just B of x p nu t perturbed by delta x. So Ex minus Bp, Bx P nu is B of x at nu minus delta x, P of nu minus delta x, minus B of x given nu, P of nu given t, which is from the outflow, which I've just written as 1 because I've taken out the B comma P. And for the death rates, we can do something similar. Both of these terms, this death rate and this probability, is in terms of nu plus delta x, which in the step operator notation is E plus of x applied to this product dp. And once again, the outflow is just the same population. It is d of x given nu, p of nu comma t. And in both of these terms, there is an integral. So there is an integral outside. And this, in principle, describes our population. This is our master equation. Notice that this master equation now has an integral in it. It is also in terms of this p of nu comma t, which is non-negligible to write down. But nevertheless, we have an equation. We would like, as I mentioned, to try to approximate this population with some continuous function, which I will call a field, so that we can deal with this field with the hopes that we can deal with this field more easily. So how can we do this? Well, here's an idea. Let's assume, as before, that there is a system size parameter and try to Taylor expand. What does this look like? It means that we will assume that, as before, that there is a carrying capacity K, which puts a bound on population growth, such that if the total population size is greater than K, the growth rate is expected to be negative. And what we really want is that the total population size, which is integral of nu over the entire trade space, is of order K. We can then transition to population density, which I will call phi, by dividing the population number function by K. Again, phi here is a field or a function. It is not a number. It is a sum of Dirac masses, each of which is scaled by K. As we did for the discrete case, I will assume that the process in population numbers is such that I can rescale to find these order 1 functions bk and dk, which describe the rate at point x trait value in a population phi, which now is population densities. And this thing is order 1. That is, this b of x given nu is order k, such that if I scale it down by k, I get an order 1 function. So that the population density, if I integrate over the entire trade space, remains of order 1. What we are doing here is, just like we did for discrete traits, we are moving from a population that transitions in units of a Dirac delta to a population that transitions in units of a Dirac delta scaled by k. And the hope is we can approximate this by something continuous. Can we? Well, we can try. Let's first try to rewrite the process in terms of population densities. Here's the master equation I just wrote down. Let's now try to rewrite this master equation. Here are the substitutions that I had pointed out. First, phi is just nu by k. It is the population number divided by this system size parameter. And the birth and death rates are the birth and death rates for population numbers scaled by k. Now, let's see what happens to each of these terms. P of nu comma t cannot change because it is a probability of finding the population in a state nu. And you are just rescaling the population by a constant. And so this should just affect the normalization constant of any probability. So P of nu comma t should be the same as P of phi comma t, except now P of phi comma t takes values in a slightly different function space. Our birth rates, B of x given nu, if I just transpose this k, is k times bk, and the death rate, similarly, d of x given nu, is k times dk of x given phi. I also need to rescale my step operators because the step operators e plus and minus describe how anything it acts on changes in terms of a single Dirac mass. But in terms of population densities, the population transitions in units of delta by k. And so we can just define new step operators, which I've called capital delta plus or minus, which describe, given any functional, how this functional would have behaved if the population differed by delta by k. And in these terms, we can rewrite the master equation. Here, P of phi t is the same as P of nu t. It cannot change. K times bk is b of x given nu. And k times dk of x given phi is d of x given nu by our assumption. And we have changed our step operators accordingly. What we have done here is moved from a population which transitions in units of delta x to a population which transitions in units of delta x by k. And for the discrete case, once we had this, we were able to Taylor expand. The idea was if there we had x to x plus minus 1 by k, and we said if k is large, this is a small perturbation of x, so we can Taylor expand. We would like to do the same thing here, but there is a problem, a slight problem. The problem is that this small perturbation in this case is not a number. In equations, if we have a real function f, little f, and we want to evaluate something like f of x plus minus 1 by k, we know how to do this. We can do this by Taylor expanding, and the Taylor expansion says that f at x plus minus 1 by k is f at x plus this perturbation times the sensitivity of f to change, which is df by dx, and higher order terms. But this is not what we have here. Our step operators bk and dk are small perturbations of a function phi. It is not the small perturbation of a number, right? And in particular, our perturbation is also a function. Delta by k is a function. So what we want is not this sort of formula. Instead, we want, given a functional or operator from a function space to the reals, we want to know, can we write f of phi plus minus delta by k as f of phi plus something when k is large? Well, can we? It's a good question. Notice that what we wanted here, what was crucial in describing this expansion, is knowing how little f changes if I change the output by a small amount. This is df by dx. The idea is if I change this x by a very small amount, how much does f change? I find this, then I scale it by the amount at which x is actually changing, and I say, okay, this is a good approximation. And the same idea applies for higher orders as well. So we would want to know how this mathcal f changes if I change the input function by a small amount. So the idea is, do we have something like a derivative for functions of functions? That is, can we differentiate, instead of differentiating with respect to a number, can we differentiate with respect to a function? This is a good question. And let's start from first principles. We have a real function, little f. We know how to define the derivative. This is what we all learn in high school, undergraduate, something like this. We learned that the derivative df by dx can be defined as follows. You look at f at a point that is slightly far away from x. Then you look at how much f has changed in this interval and you scale it by the amount your input has changed. So you say, if I change the input from x to x plus h, this is by an amount h, how much does the output f change? And then I make this perturbation very, very, very small. And I say this is the derivative. If I have a multivariate function, capital F, can we differentiate with respect to a vector? Well, yes, we can. The definition most of us first see is of a partial derivative. And the idea of the partial derivative is, similarly, if I have an input, capital X, now a vector, and I change the output by a very, very, very small amount in a particular direction, here ei is a unit vector that is 0 everywhere except at the ith location, then I will know how capital F is changing in the direction xi. Because here, since everything else is a constant, I go back to my first definition here. I am essentially changing this bold x in the direction, the ith direction, by a very small amount. We then say that we can define the notion of a gradient, which is typically denoted by nabla, by saying that the ith component is how much f changes in the ith direction. This is a way of differentiating with respect to a vector, but there is some more general notion which I will try to illustrate, and it only occurs in higher dimensions. If I have a one-dimensional function little f, and I ask you what is the derivative at some particular point, you don't have, you know exactly how to do it geometrically. You draw a tangent and you say the slope of this line is df by dx, and that's all you have, right? X is the only parameter that little f takes, and so there is only one notion of derivative here. But let's look at something slightly more complicated. Let's look at a two-dimensional function now, f of x comma y. In this case, what I just showed you, the partial derivative, can be viewed geometrically like this. I draw a vector that is tangent to this function and parallel to the y-axis and say, okay, the slope of this line is the partial derivative with respect to y. Similarly, if I was to draw a tangent here that is parallel to the x-axis, at the same point, the slope of that line is dou f by dou x at that point. But in two dimensions, we have more choice. There is nothing special about x and y. This is just some choice of basis. And I might want to know, how does f change along some arbitrary vector v? Is there an idea of what this is? That is, if I draw a tangent parallel to v and compute the slope of this tangent, what is this? This has a name. The name is called a directional derivative. The math people denote it as d, capital D sub v of f, and you're supposed to read it as the directional derivative of the function f along the vector v. And this is a measure of how much f changes along this v, if you perturb it along this unit vector v. Mathematically, one can write down what this is. If I have an n-dimensional function, capital F, the directional derivative of f along v can be found by taking the dot product of v with the gradient. And this is intuitive, sort of, because the gradient is sort of how sensitive f is to change, and v is the direction along which you want to change it. And if I write this down component wise, it just means that if I look at how much f changes along the ith direction and multiply it with vi, which is how much I am perturbing in the ith direction. And it turns out that this definition is exactly equivalent to what you might expect from a first principles definition. That is, if I take f and perturb it in the direction v by a very small amount h, and I ask how sensitive is capital F to this change, this looks like a derivative, right? If I did not have v, this would be the single dimensional derivative. And it turns out that this directional derivative exactly equals this limit. So it's exactly what you would expect a derivative to do, which is it approximates f given a very small perturbation. Interestingly, and this is where our functional derivatives are going to come in, this is also a way to characterize the partial derivatives or the gradient backwards. That is, if I had some function a such that for every vector v dot a gives me this limit, then a must be the gradient. This is a way to characterize the gradient indirectly. And we want this because when we have infinite dimensions, all our characterizations are indirect. For example, our delta, our Dirac masses were all characterized indirectly. So here's an idea. If I have a function, a functional from a function space to the reals, maybe I can characterize how this changes. I will denote this by dou f by dou rho, which you are supposed to read how does f change as I change the input rho. This is called a functional derivative because it's derivative of a functional with respect to a function. And the idea is I will characterize this indirectly because I know that if I have this summation, I get a nice notion of what derivative should be in terms of limits. So I will characterize it as follows. If I have any function xi, which is nice, dou f by dou rho is uniquely defined as a function such that if I integrate it with xi, I will get something like a directional derivative in the direction of xi. This is all in quotes because these are all infinite dimensional things, but you can maybe see the analogy here. If I informally let, well, a function, firstly, maybe you can think of as an infinite dimensional vector loosely. And loosely here, if I let the number of dimensions tend to infinity and replace this sum with an integral, I can just match terms. For every v here is xi. The summation of dou f by dou xi times vi, which is the integral now of the functional derivative of f with respect to rho at the point x times xi of x, is the limit, which is a normal derivative type limit, f of rho plus h xi minus f of rho by h. This is telling me if I had an input rho and I perturb this input by an amount xi scaled by some small parameter h, how much does capital F change? And the idea is this should hold for every xi. That is, it should be independent of the choice of this xi. Well, it need not, but the idea is dou f by dou rho should obey this equality always. And you can think of dou f by dou rho at x, which is my notation here, as equivalent to dou f by dou xi, because when I have a function, the index, which was I here, becomes continuous. So the index is just the argument of the function rho. This is a somewhat hand wavy but good notion of what a functional derivative should do. The study of these sort of things is called calculus of variations. It turns up in physics. It's also called functional analysis. It turns up in mathematics. And we can now talk about what we initially wanted, which was a Taylor expansion. If I have a single variable function, little f, I know how to Taylor expand it. The Taylor expansion says f of a plus x is f of a plus perturbation times this sensitivity dou f by dou x and higher order analogues of the same. If I have a multi-dimensional function, capital F, I can do the same thing. Notice that what turns up in the Taylor expansion, this xi times dou f by dou xi, is precisely the directional derivative. It is not the gradient. It is the gradient times the perturbation. That is, I am asking in multiple dimensions, if I perturb by a vector x, how much does f change along the vector x, which is given by xi times dou f by dou xi, which is the sensitivity of f to change in the ith direction times the change in the ith direction. And the higher order term looks similar. Now we have mixed derivatives, which is why there are two summations and things look a little scarier. And you have more and more summations as we go to higher orders. This gives us a clue for what we should have for functions. If I have a function from some function space to R, I might therefore guess this sort of form where I say that f at rho naught plus rho is f at rho naught plus the directional derivative analog along rho, which is integral of rho dou f by dou rho naught, where this dou is the functional derivative, plus a double integral, and so on. And informally, as I mentioned before, if you take the number of dimensions to infinity in this multi-dimensional function and replace a sum by an integral, this term becomes that term, this term becomes this term, and so on. But again, this is little informal. And it turns out that this can be made precise. And this sort of formula sort of generally holds. And this concludes our mathematical interlude. We can now go back to our actual problem at hand. We had this functional master equation for our quantitative traits. And these step operators, delta of x, which takes the population phi and tells me what phi would have been if the population was delta x by k apart. We can now use what I just showed you, which is our Taylor expansion formula, which answers my initial question, which is, can I write this as f of phi plus something? Here the relevant things are rho naught is phi and rho is delta by k. And we can therefore just substitute this. If I substitute, here just rho naught equals phi and rho equals delta x. Here's what we get. F of phi plus 1 by k, which is from here, times the integral dou f by dou phi times delta x integrated over y, plus there are two k's here because it's rho x times rho y, so it's 1 by 2 k square, double integral dou square f by dou phi, evaluated two different points, mind you, plus so on. And I'm not going to write the higher order terms. Can we evaluate this? Well, yes, because by our definition, our Dirac mass obeys the following rule. If I have any nice function f, integral of f times delta x gives me f of x if x is in A and 0 if x is not in A. Now I am integrating over the entire trait space. And since any given individual must have a trait value somewhere in this trait space, this case is never going to happen. I am instead going to get this inside functional derivative evaluated at the point x. This is from the definition. This is also true here. You just have to do it twice. And so for example, the first integral removes this y variable and you get dou square f by dou phi x, and the second integral turns phi z into phi x. So if I just use the definition of the Dirac mass, I get f of phi plus minus 1 by k. This integral dou f by dou phi times delta x is dou f by dou phi of x plus 1 by 2 k square dou square f by dou phi dou z which becomes dou square f by dou phi square, plus so on. By the way, you might wonder, especially I think if your Vidya was on this call, why it is legal to use this formula, because this is true for smooth functions, and dou f by dou phi we know nothing about. But the justification is that when we assume we can Taylor expand, this requires f to be smooth. In particular, it requires f to be what's called C infinity. And if f is smooth, its first derivative is also smooth and its second derivative is also smooth, just because we need infinitely many smooth continuous derivatives to be able to Taylor expand, which is why these substitutions are legal. So we have some expression here. We can now subtract f of phi from both sides, because what turns up in the master equation is not delta plus minus, but delta minus minus 1 and delta plus minus 1. So if I just subtract mathcal f of phi from both sides, here's what happens. I get delta plus minus minus 1 is, there is a sign here, 1 by k times the first derivative with respect to phi, plus 1 by 2k square times the second derivative with respect to phi, and higher order moments, all applied to mathcal f. And I am going to neglect these higher order moments. I'm going to work only to the highest order. Let's substitute. For the first term, we have delta minus minus 1. The entire thing is applied to b times p. And by our formula, this must be minus 1 by k dou by dou phi, which is here, plus 1 by 2k square dou square by dou phi square, which is here. Whole thing applied to what was outside. F here is b times b. And I have just written out this integral in full. For the second term, we have delta plus minus 1, which is plus 1 by k dou by dou phi, plus 1 by 2k square dou square by dou phi square, which is what is inside these parentheses. The whole thing is applied now to dk times p, which takes the role of mathcal f. We can rearrange this slightly. Firstly, note that there is a factor of k outside and a factor of at least 1 by k inside. So we can remove one of these k's. We can also group such that all the first derivatives are in one term and all the second derivatives are in another term. If we do this, we will arrive at this equation. We can just check that it's the same. Here we have minus dou by dou phi applied to bp, and here it is minus dou by dou phi applied to bk times p, which is outside, plus dou by dou phi applied to d, which I have written with another minus sign outside. This minus into minus becomes plus dou by dou phi applied to d, sorry. And for the second derivatives, the signs are the same. There is a plus 1 by 2k here and a plus 1 by 2k here. So it's b plus d inside. Let's now stare at this equation for a second. This equation looks sort of like a Fokker-Planck equation. In particular, our finite dimensional Fokker-Planck equation looks like this. It's a PDE for the probability of finding the population at a vector x at time t. And this Fokker-Planck equation looks like summation of the first derivative of some function f times p plus the second derivative times some function g. And I assume that g is of the form something by k. This is just to make the constant factors explicit. So this looks like a functional Fokker-Planck equation. Informally, if I take the number of dimensions to infinity in this finite dimensional Fokker-Planck, I should get what this is. But what we used for our gaining insights into ecology and evolution was not the Fokker-Planck, but the fact that every Fokker-Planck corresponds to a stochastic differential equation. We said that a Fokker-Planck equation that looks like this, with fi in the first derivative and gi in the second derivative, corresponds to a stochastic differential equation with fi in the drift term and root gi in the diffusion term. Here WTFI is a Wiener process, and for each I it's an independent Wiener process. Can we make some sort of analogy here? Well, maybe. If you just do it naively, we should get something infinite dimensional, right? It's a stochastic differential equation with infinitely many indices, and in particular the index here is continuous. What this means is that it is a stochastic partial differential equation, or an SPDE, and the SPDE is exactly what you would expect. Here's a drift term bk minus dk, and there is now a square root here, so it's 1 by root k times square root of bk plus dk times something, and I will explain what this something is in a slide or so. I would like to note that for finite dimensional equations, that is, if I have this sort of Fokker-Planck and this sort of stochastic differential equation, this equivalence is very well known, it's very well understood. People see it everywhere. You will see it in sort of all your StatMech textbooks. But this infinite dimensional case, that is, whether a functional Fokker-Planck equation corresponds to an SPDE, is less clear. We know that this sort of thing works if our function space, which I had called M, remember, that is the space of phi which is allowed, is nice. In particular, if it's something called a Hilbert space. If you don't know what that is, don't worry about it. It's just sort of a very nice, well-behaved function space. But in general, we don't know when this can happen, in that we do not know if the space is not a Hilbert space, whether it is necessarily not true or whether it is still true. We just don't have the mathematical tools to know these things. I am not going to worry about the mathematical tools. I'm just going to assume that this is true. And I will maybe explain what this SPDE is. The first term is clear. The first term is the deterministic aspect, as before, in the sense that if I just ignore, if I take k to infinity, I get a PDE now, which says that this density field phi is given by bk minus dk. Notice that when we write down Fokker-Planck equations or SPDEs, the solutions to these things are nice. And so this is truly a field in the sense that if there's a solution, typically it's going to be continuous. But I did not explain to you what this W dot was. W dot is something called a space-time white noise, and it's defined indirectly, as is you're perhaps getting a feel that everything in these infinite dimensions is defined indirectly, and it's defined as follows. If I have any two functions f and g such that they are square integrable, meaning integral of f square and integral of g square is finite, and any time t, then this equality holds. This says that if I take the product f times w dot, integrate over the trait space and integrate over time, and take an expectation, I get 0. And if I have two functions and I try to do this, I do not get 0. Instead, if I take an expectation of integral of f w dot and integral g w dot, I get fg. You can think of this sort of as saying that if I take expectation, this w dot disappears, right? So this should remind you maybe of the purely temporal white noise, eta, and on the math side, eta is defined as follows. If I have any two functions f and g such that their integrals are finite and any time t, the following should hold. If I take an expectation of integral of f times eta, I get 0. And if I have two functions f and g and I take this product of integrals, I should get integral of fg ds. In physics literature, This is not the definition you typically see. The definition you typically see is what happens if I put f equals g equals 1 here, which is eta of t is expected to be 0 if I just put f equals 1, and eta square of t, which is an informal way of writing integral eta as integral eta square, is dt. If you were to try to use the same notation for physics, for the space-time white noise, you would get, I think, the following, that w dot expected is 0 and w dot square is dx dt. But take this with a pinch of salt because I am not familiar with physics notation. So it is very possible that I have I've misunderstood something wrong with the notation here. But this left hand side in terms of expectations and integrals is the right thing. This gives us now a continuous description of how our density field changes in terms of a stochastic partial differential equation. Let me give you an example to see what this sort of pipeline might look like using asexual resource competition. In the discrete case, that is at the exact individual level, let's assume that this is the birth and death rate we have. And I will explain what this is supposed to mean. If I have a population nu, the birth rate at the point x is given by the integral of e to the minus x minus y square times nu dy. How you should think of this is individuals are asexual. They give birth to offspring with mutations. The effect of these mutations, that is how far away the mutant is from the parent, is a normal distribution. This is an exponential of minus x minus y square. And this is the variance of the distribution. So most often, I've just omitted the normalization constant because it doesn't matter. Most of the time, you give birth to offspring that have the same phenotype as you, but you can give birth to offspring that are further away. This distance x minus y is all that matters. And since it's squared, you are equally likely to give birth to offspring that have phenotype greater than yours or less than yours. With beak length, you can think of it as longer beak length or shorter beak length. And so this birth is supposed to model this sort of mutation. The idea is you take exponential of this mutation kernel, exponential of minus x minus y square, multiply it with the current density at y, which nu will give you this, remember, because this integral of m nu is just summation of m evaluated for each individual, and you have what you want. For death rate, I assume that there is some resource competition. And in particular, I am going to assume that the death rate of a phenotype X at a point nu is given by the existing density, which is nu, times the integral of alpha times nu, where alpha xy is the effect on the death rate at type X due to individuals of type Y. And this is supposed to be a competition kernel. I am not going to specify its functional form just yet, but you can think of this as being analogous to Lotka-Volterra competition, which is why I've used alpha. The idea is this is the continuous time analog of alpha x, alpha ij nj is alpha xy nu y, which is what this integral, and the summation is replaced by an integral. Let's try to use our pipeline. Here everything is discrete. We have Dirac masses. Let's first move to population density space using the substitution phi equals nu by k. By the way, notice that I have included this k explicitly in my model definition. This is typically what will happen when I pick a particular model. You will find a system size parameter in the definitions of the birth and death rates. This is what our assumption means explicitly. If I now rescale my birth and death rates and densities, I can substitute. This nu becomes k times phi, and this b becomes k times bk, and the k's cancel out. So bk now is mxy phi yt dy, And I have switched notation to make phi an argument of two things to show that it's a field now. It's supposed to be continuous. So phi of y is something that makes sense. And dk by the same argument becomes phi of xt. Here this new is k times phi, and you can cancel it with the k below. This new is also k times phi, and d is k times dk, and you can cancel the two dk's to get the birth and death rates in density space. I will use a small approximation just for illustrative purposes. If this variance is small, that is, if most births are without mutations and those with mutations are very close to phenotype values, I can approximate integral using standard Taylor expansion as phi of xt plus sigma square by 2, this variance by 2, dou square phi by dou x square, and I'm going to neglect these higher moments. And I'm just going to use this to connect our model with some familiar models. Let's now write the SPDE. Remember, the drift term is birth minus death. The diffusion term is birth plus death. So I've just regrouped. Here I have birth minus death is phi minus phi times alpha phi dy integrated, which I can take out of phi to make it phi times integral 1 minus integral of alpha. And I've just changed notation from dou square phi by dou x square to the Laplacian, which I've denoted by delta square. And here we have birth plus death, which the same idea. This is phi plus phi alpha, which is phi into 1 plus alpha, plus this sigma square by 2 dou square phi by dou x square times w dot. And this is now a field, that is phi of xt will have continuous solutions. And so this is some continuous distribution. Let's stare at this equation for a second. Now, if I neglect demographic stochasticity, this equation has a name. It's something called a quantitative logistic equation, sometimes also called quantitative Lotka-Volterra, because it should look a lot like the logistic equation or the Lotka-Volterra equation. Remember, the Lotka-Volterra equation is ni times 1 minus summation alpha ij nj. Which, if I just informally make it a quantitative trait, becomes phi into 1 minus integral alpha xy phi y. And mutations are modeled here as diffusion across the trait space. But for finite populations, our derivation predicts that we have an extra term. This extra term is a space-time white noise that is scaled and depends on the sum of the birth and death rates, which in this case becomes phi times 1 plus this competition term, and the mutation acts the same way. If I take another limit, which is if I assume that all competition is only among members that have the same phenotype. So a good example is maybe space, where I only care about people who are in the same spatial location as me, if I coarse grain enough. And the question is, what happens to this then? A good example then might be to replace alpha xy with a Dirac delta to say, remember alpha xy is the effect of y on x. And by saying that it is delta x, I am saying that y affects x if and only if they are the same. And of course, you can scale it by a constant to or some functional form. But for simplicity, let's assume it's just this. If x and y are the same phenotype, there is some death rate effect. Otherwise, there is not. If I substitute this and use the definition of a Dirac delta, remember alpha xy phi y then becomes delta x times phi y integrated over y, which is phi of x. We arrive at another PDE. Now this PDE looks simpler than that PDE. And if I just ignore these noise, take the infinite population limit, k to infinity, we arrive at a famous equation called the Fisher-KPP equation. This is supposed to describe spatial dynamics in one dimension, and it is easy to see why this assumption that competition is only within phenotype is a good assumption for spatial dynamics. So this again looks like a logistic equation. This looks like x into 1 minus x. And this is a mutation term, which is modeled as diffusion across state space. But once again, for finite populations, we don't get this. Instead, we get some SPDE, which is the Fisher KPP plus a stochastic term. And this thing can, in general, need not behave the same way as just this. Because just like for discrete cases, the variance is controlled by this term. And here it is 1 plus phi instead of 1 minus phi. And just like for discrete cases, notice that I could have started out with multiple different microscopics, that is different functional forms here, to end up with the same form here, because this depends on b minus d and b plus d. And just like there, if I just had a constant here to the birth rate and the death rate, I will get the same term over here, but not inside the square root. So I can get, for example, Fisher KPP dynamics that have the same expected behavior, but very different variance. This is hopefully a little enlightening on what exactly we're doing. I will start wrapping up with just one more technical thing, which is to do any sort of calculations.
Can I just ask a quick question?
Yes.
Shikhara? Did you
Yes.
solve that stochastic Fisher equation?
No.
You haven't. Okay.
No. I just wanted to illustrate that it can be derived.
Okay.
But so
in your manuscript, do you illustrate when you are illustrating derivations, but are you also solving and checking whether the solution of the SPDE numerically matches with the let's say stochastic individual based simulations?
So I have not done this so far for two reasons. One is that my entire manuscript right now, the pitch is that I want to look at these fundamental theorems and how to formulate it. And this is sort of a heuristic approach, the whole Taylor expansion and so on, to a rigorous measure-theoretic approach by Week et al.
Yeah.
And their approach, like they get the same equations that we get. And they have shown that their equations are consistent with individual based models.
Oh, okay.
And so sort of by transitivity,
sort of
it should work.
on that too, not to worry about the last part. Okay.
Yeah.
Okay. Sounds good.
Also, I think these are sort of often, if I have complicated things, this sort of W dot becomes very hard to solve. This is my understanding. Yeah. I just before I wrap up, to do any sort of calculations with these sort of things, you need an etho formula. In particular, if I wanted to study evolution, for example, if instead of densities I move to frequencies, I need an etho formula. But how do you formulate an etho formula for this W dot? Well, let's first recall what ethos formula looks like for finite dimensions. Ethos formula says the following. If I have an n-dimensional process x that is given by fi, whose ith component is given by fi dt plus summation gij dwtj for some matrix jij and some vector fi, and if I have a nice function h from Rn to R such that and I want to know how h of x behaves. That is, if I change variables of x to h of x, if I want to know how h of x behaves, ethos formula looks like this. I did not show this on the board because it can look a little scary because it has a lot of summations. But the idea is that the important term is this extra term over here. Otherwise, it is chain rule, but there is an extra term that occurs because dwt is dt, roughly speaking. And this is ethos formula, and it is like incredibly useful. What do we expect for SPDEs? Well, let's say I have an SPDE that looks like this. It's slightly more complicated than what I had. So if I had dou phi by dou t equals mathcal f of phi comma x plus integral g phi xy w dot yt dy. This thing is now my space-time white noise, which is the continuous time analog of this. And if I had something like this, question is what might you expect? And if I have a function h that takes in this function space and outputs a real number, so some operator, what might I expect to be able to say for dh? And here's what the ethos formula looks like. Again, it's a little scary because there are lots of integrals, but this equation is informally, if I take n to infinity in my finite dimensional ethos formula, this summation becomes an integral. So instead of fi dou h by dou xi, I would get integral f dou h by dou phi, because this index is now a function. And here this double summation becomes a double integral. This summation becomes an integral, and so on. And this is a suitable candidate for an ethos formula for SPDEs. Again, the caveat is that while we know this finite dimensional ethos formula very well, we can prove that it always holds for these sort of stochastic processes. For infinite dimensions, for SPDEs or infinite dimensional Brownian motions, it is a lot less clear when this formula holds. We know, well, we as in the human race knows that this formula is true if this M is a nice space, if it's something called a Hilbert space, and these F, G, and H, all three of these operators are nice operators, something called Hilbert-Schmidt operators. But in general, we don't know. We don't know whether this formula holds. By which I mean to say that we also don't know that it doesn't hold. We just can't make much progress mathematically without assumptions on this. But of course, this is the sort of thing that has never stopped physicists. And in this spirit, I'm not going to let it stop me. And I'm just going to assume that this formula is true for our case. And if we assume that it's true, we can study evolution. And I will show you one quick consequence. And I'm not going to take you through the derivations, because the derivations then are, if I want to go to trait frequencies, P, which now is x by integral x, or phi by integral phi, I have to use ethos formula. And I can maybe do it in detail sometime, but it's just tedious calculation. You need to calculate what this dou h by dou phi is, what these things are, and all these functional derivative calculations are more complicated than normal derivative calculations because these are defined indirectly. So you need to use some tricks to calculate them, but you can do it. But I will show you a consequence, and for the first time, make a slightly more concrete assumption on the birth and death rates. I will assume for now that the BK and DK, that is the birth and death rates in density space, can be written as current density times some function. That is, the total density birth rate is the current density at that point times some function, which I've denoted B int because it's supposed to represent the individual or per capita birth rate at the point X, and similarly for the death rate. Given these, I can define suitable notions of per capita growth rate or Malthusian fitness W, which is the difference between these per capita birth and death rates, and tau, which are called per capita turnover, which is the sum of the birth and death rates. In these definitions, you can derive things like the replicator-mutator equation and the price equation for quantitative traits. I'm not going to show you those. I am going to show you something that occurs in the strong selection weak mutation limit. This is a limit that theorists like because you can get nice predictions. And the limit is the following. First, we assume that mutations are rare in the sense that the mutation rate is very small. We also assume that mutational effects are small. That is, mutants are very close to their parents. This is sometimes called almost faithful reproduction. And then we assume that selection is strong in the sense that if types that have low relative fitness are immediately eliminated. So a type either reaches fixation or eliminates or just goes extinct on the timescales we look at. And so the population looks like it is very sharply peaked around a few small trait values. This is what I mean by strong selection in this case. In this case, we can mathematically write, because of the strong selection assumption and these rare and small mutational effects, we can assume that our population is essentially monomorphic. That is, phi of xt is some scaling that you can ignore times a Dirac delta that is moving across state space according to some trajectory y of t. And we would like to know y of t. And so the approximation then is everybody in the population has the same phenotype, but what this phenotype is changing. That is, if there is a new mutant that arises, it either immediately fixes in the population and everybody adopts this new mutation, this new trait value, or it goes extinct. And you can think of this as observing the population at sort of long time scales if you prefer. In this limit, you can derive, using the etho calculus I showed you, an equation for this y of t, and the equation looks like this. It says that how yt changes is given by the standing genetic variation, which I denoted sigma square x, times some gradient, which I've called here the finite population selection gradient, and I will tell you what this is, plus something describing stochastic fluctuations. This first term, dou g dou x, is the derivative of something I've denoted g of x given y, and it is calculated the following way. For a trait x, you look at what the fitness of x would be if everybody in the population had trait y. This is this. You can ignore the scaling for these purposes. This gives you w of x. Right? This is the fitness of a mutant x in a population y. It's sometimes called an invasion fitness. But there is also a second term, 1 by knk times the turnover rate of a mutant x in the population y. This is also why I think the bar notation is helpful, because it helps you read what this is. And the stochastic fluctuations are something that looks a lot like a variance. It is x minus y. Notice that because of this Dirac delta assumption, y is the same as x bar, because everybody has trait y, times something, times w dot. And you can notice, if it makes you happy, that this is a Brownian motion, because it is space-time white noise integrated over space. So this is just a standard Wiener process. I just have not written it that way. If I take the infinite population limit of this equation, I get this disappears and this disappears. There is a 1 by root k here, by the way. Because this second term disappears, I get sigma square x times dou w dou x. And this is a famous equation in quantitative genetics. People call it Lande's gradient equation. And the idea is that the population y follows a fitness gradient. It moves such that it moves towards higher values of invasion fitness in particular. That is, when the population is at y, it looks around itself and asks if wx given delta y is positive, if there is a mutant close by, close to y, sorry, that has positive invasion fitness, everybody adopts this trait. And the rate is scaled by how much variance there is around y, which we assume is very, very, very small, but non-zero. This is also, if you know some adaptive dynamics, should look like the canonical equation of adaptive dynamics. And they are actually very closely related. But what we learn is that for finite populations, in the same limit, while you might expect to follow a fitness gradient because you have very strong selection and weak mutation. Or naively you might say, okay, there's drift, so I don't follow a gradient exactly. You find that your mean trajectory, that is if I take expectations, I do follow a gradient, that is it is d by dx of something. But this gradient is not just a fitness gradient. It is fitness plus something or minus something. And this something is called noise-induced selection because it is selection for lower tau because of this minus sign. And it is scaled by k of t, which is the total population size. I will wrap up here. I think I will just tell you that if we also consider mutation, then that is if we say that this birth rate is per capita times b plus some possible influx term, then derive a replicator-mutator equation, which also one can show is equivalent to the Kimura-Crow equation. Here S is supposed to be selection mutation balance. So it is for a given quantity F, it is F minus F bar times the frequency, which is what selection looks like. So SW is selection for fitness, W minus W bar times P, plus some mutation term. And there is selection mutation for turnover rates, which is noise induced, plus some stochastic fluctuations. One can also derive a price equation, which looks like this. It's for the mean value of some function in the rate, some function of the population. And if you take k to infinity, you recover the classic price equation, which is just covariance of W with F plus this thing. And I will stop here. I'm not going to go into details about any of these equations or how to derive them, but they are straightforward in that you use Ito's formula and some algebra, and you will arrive at these equations. If you want to see those details, you can go to the manuscript. You can use this QR code, or you can just ask me. Everybody here knows how to contact me, but since this is being recorded, if at some point someone sees this, you can contact me on any of these platforms. I should still be available on them. And thank you for listening.